Guess we'll go ahead and get started. Folks at home, you can hear me okay? If you can't, let me know in the chat. Just one or two housekeeping items. On Learning Suite, it should now be enabled for you to go back in and look at your exam, your responses, what the correct answers were. For most of the questions, I've uploaded videos that explain why the right answer is right. Apparently, this is an underused feature of Learning Suite. They said they've never had somebody try to put a video in the feedback before, and it's caused some challenges. The matching questions, I still can't figure out how to get a video uploaded. It breaks the exam question on my end if I do that. So there aren't videos yet for that. And somebody mentioned in the chat last time that they were having trouble with the video from question 22. So it's possible there's going to be some technical difficulties. Hopefully they'll just make it better, but I don't know what the time frame on that is. I would like the ability to share videos privately with folks who have taken the exam and prevent them from being sort of out there in the internet so that anybody can see them. If you know of a way to make that happen, if you could just let me know. I know you can do it on YouTube, but that would involve me typing in each of your email addresses one by one, which seems like a bad choice. So if there are some options that you guys know for that, I'd be interested in hearing them. If you're concerned about your exam score and have questions, start with the Exam 1 advice video on my YouTube channel. That gives you basically what I would say to you if you were to come into my office and say, I didn't do as well on the exam as I thought I had done or thought I would do. So start there, then look at the videos for each of the questions that you got wrong. If you want to meet one-on-one after that, I've made time available starting tomorrow through the end of the week. 10-minute slots starting basically at 9 and ending whenever I get tired. I forgot to, don't anybody sign up for Wednesday afternoon. I have to go home and take care of kids that day. Amber's got classes. She's in a master's program here. She's got classes in the afternoon, and so I'm on after school duty on Wednesday afternoon. So if you signed up there, I'm sorry. I'm going to delete your entry and get rid of it, and you'll have to sign up again. But other than me, everybody in the class should be good humans. Don't delete other people's entries. And I'll try to meet with as many of you as want to. Via Zoom is probably the easiest thing to do. There are 10-minute slots now. I anticipated some demand, but if there's no demand, you're welcome to go over the 10-minute time. So in any case, that's it, I think, for Exam 1. Anything else you guys want to ask? Oh, you can get the link to the Google Sheet to sign up for those slots in the most recent announcement on the Learning Suite page for the course. I don't know whether or not an email went out about that announcement. If it didn't, you can just go and click on announcements and you'll see it. All right, I think last time we were talking about conformations about sigma bonds, and we had made the butane conformation situation a little more difficult by adding an OH group to one of the two carbons. So now we've got 2-butanol instead of just regular butane. And I wanted you to think through which of these staggered conformations would be better and which of the eclipsed conformations would be worse. So, what do you got? Any of the staggered conformations you think would be great or particularly bad? Sure, go ahead.
I imagine the S3 with the CH3 between the OH and the CH3 to be particularly not energy.
Okay.
Energy.
Yeah, so you expect some significant torsional strain there because you have a methyl group and an OH group that are gauche to each other. And then that same methyl group in the front is also gauche to another methyl group. whereas each of the other conformations only has one gauche situation and one anti-situation. So I'm just sort of writing down all the times you've got non-hydrogen things gauche to each other versus non-hydrogen things anti to each other. So among those, we agree that staggered 3 is probably the yuckest one, least stable, most strained. Okay. How about S1 versus S2? Go ahead.
I think S1's probably the second most yucky, just
Okay.
because CH3s are bigger than OH, and so they would repel each other more.
So yuck, ear, sure. Because, wait, which one did you? You said S1 is yuckier because of the two, because, okay, right. So why, that's based on the conclusion that having two methyls gauche is worse than having methyl and hydroxyl gauche. So why is that? Anybody know? Why would it be worse to have two methyls gauche to each other versus a methyl and a hydroxyl? Go ahead.
Does the oxygen hydroxyl draw some of the positive charge from the hydrogens? And that would kind of make it a little more favorable?
So it is true that oxygen is more electronegative than carbon, and it's if you have enough oxygen atoms, that effect can actually be important and interesting, though for this particular case, it has to do more with size. So, do you have your hand up?
Yeah, I was just kind of going back and forth thinking that oxygen is bigger, so that could be worse. But
Okay.
at the same time, this CH3 has all those hydrogens, so
Okay.
electron cloud would be larger.
Right. So the response here in class was that methyl, you've got a sp3 hybridized tetrahedral carbon bonded to 4 different things, 3 of them hydrogens, and no matter which way you spin around this bond, you've got hydrogens in the same places. With the OH group, you've got 2 lone pairs on that oxygen, but the only bond you have other than with the other group here is an oxygen-hydrogen bond. And if you swing around there, you can probably get that one out of the way. In terms of size of oxygen versus carbon, you did say something that I wanted to check on, just because I don't want it to be a stumbling block in the future. Carbon and oxygen are in the same row of the periodic table. Oxygen does have a larger atomic weight, but its radius is actually a little smaller than that of carbon, because radius goes down as you go from left to right. As the nucleus gets more charged, the electrons get pulled tighter in. Though the difference in size is not enough to make a big deal here, and you can think of them as being basically the same size. The bigger difference is methyl groups got more carbon-hydrogen bonds. Okay, other questions? Okay, so I am sorry, yeah, somebody's noting that I wrote something incorrectly there. Yeah, for staggered 1, the methyl and the hydroxyl are anti, and for staggered 2, the methyl and methyl are anti. So yeah, it is worse because in terms of size, and when you're talking about atoms, when you're talking about size, what you really are talking about is the electron cloud surrounding the atoms. And steric hindrance comes from electron repulsion between those clouds. And so, yeah, methyl is bigger in that sense than the hydroxyl group is. So we would predict, yeah, staggered 2 should be least yuck. All right? Do any of you, I don't know if you remember, probably not, probably this was a thing of the 80s, but there used to be a campaign from Poison Control involving these stickers which you would get and you would put on things like, because back in the 80s, you would store all kinds of hazardous chemicals under the sink, and so you would put this sticker on them, Mr. Yuck, with his tongue sticking out or something to indicate you weren't supposed to drink that. I don't know if, no, nobody knows Mr. Yuck. Okay, Google it. Yes, somebody does. Somebody remembers Mr. Yuck. Anyway, yes, we would say staggered 2 is our least unstable, best, most stable staggered conformation. You could use similar reasoning to rank the eclipse conformations in order of stability. For example, you would predict the one where the methyls are eclipsed with each other to be worse than the other 2. All right. This brings up a point. Is there any sort of quantitative way we can assess how big a group is? And there is a way to do this, and it involves something called an A value. The name for A value comes from the fact that these numbers were derived from actually cyclohexane experiments where they measured how much worse it was to have a group axial versus equatorial, and we'll talk about that. But you can put a number on that, numbers in terms of energy that sort of give you a sense for how large a group is. For hydrogen, the value is 0. This squiggly line indicates whatever group we've attached to something else. A hydroxyl group has about an A value of 1 kilocalorie per mole, and a methyl group has an A value of about 1.7. So in terms of energy, it's you would say that methyl appears to be almost twice as big as hydroxyl. And you can use A values to make judgment calls about whether one conformation is more stable than the other. So the take home from all of this is, if I drew a bunch of conformations for you and asked which was the most stable, which was the least stable, you should be able to do it. A word of warning, it is always possible to make up your own problem that is impossible to answer. As these things get more complicated, it stops being very clear, really, in terms of what the right answers are. So just understand that for the questions that I give you, there will be a clear answer, and the principle is you want to keep the biggest stuff furthest apart. That's not correct English, but I hope it conveys the idea. The example is that it's better to have methyl anti to methyl than to have methyl anti to the OH group. All right? Anything else on that subject? So let's talk cycloalkanes. Last time I actually spent too much time talking about cyclopropane and cyclobutane and cyclopentane. We didn't have enough time on the chair stuff, so I don't want to make that mistake this time. I want to introduce the idea of angle/ring strain, and I guess we should call it bond angle or ring strain. And this arises from differences between the ideal angle for a polygon if it were flat versus the ideal angle for an sp3 hybridized carbon. All right? So cyclopropane we can draw like this. This is our simplest cycloalkane. And cyclopropane exists. And cyclopropane rings are a part of many important natural products. Nevertheless, it is it is the most strained ring we can make. And the reason for this is that in an equilateral triangle, the bond angles are constrained by definition to be 60 degrees, right? Has to be 60 degrees. Would prefer for an sp3 hybridized carbon 109.5. So essentially we've had to take a tetrahedral methyl group kind of thing, and we've had to pinch two of the bonds closer together, distorting from the ideal bond angle. And that requires, when you have to do that, that means the orbital overlap is not perfect for bonding. If you measure the heat of formation for cyclopropane and compare it atom per atom to a cycloalkane that is not strained or a situation that doesn't have strain, you can calculate how much strain raises the energy of this molecule. Therefore what? Well, we're going to see later on that if you have a molecule with a three-membered ring and you have an option through a reasonable reaction to open that ring up, it relieves ring strain, and that can make the reaction more favorable. We'll see examples of that, I believe, in chapter 10. 9 and 10, actually. All right. Cyclobutane is the first ring where we can do something about ring strain. So I'm drawing this molecule as though we were looking down on it from above, and if the molecule were perfectly flat, that is, if all of the carbons were in the same plane, the bond angles between each carbon would have to be 90 degrees. And again, ideally, that would be 109.5. So you've got some more ring strain, though perhaps not as much as you did for cyclopropane. However, by virtue of the fact that cyclobutane has 4 atoms versus 3, there's something we can do. 3 points define a plane. So if you've got 4 points, there's no need for them to be in the same plane. And actually, cyclobutane can do something to relieve the strain, and that is called puckering. Before we talk in detail about puckering, oh, there's a chair. That's where we're going. Wait a minute, that doesn't look like a chair. No, it doesn't. 3-membered ring, you've got ring strain, and then I forgot to point out you also have torsional strain, because as you look down each of those carbon-carbon bonds, notice that all the bonds are eclipsed. Okay? So you've got high ring strain and high torsional strain. Ring strain has to do with bond angles. We can also call it angle strain. And torsional strain has to do with eclipsed versus staggered. And of course, in cyclopropane, as you've seen, all the bonds are staggered. We can relieve that in cyclobutane. And what we do there is to, let's just imagine looking at the cyclobutane ring from the side. All the carbon-carbon and carbon-hydrogen bonds are eclipsed with each other. And you're going to take the 2 carbons in blue and sort of move them downward in this puckering process. And in so doing, you generate a conformation that's no longer flat. And because it's not flat, you've relieved some of the ring strain and some of the torsional strain. I'm not going to require you to draw the puckered conformation of cyclobutane, but I do want you to have the idea that by distorting from planarity, we can relieve some of the angle and torsional strain. So I'll draw a cyclobutane for you briefly so you can see what the puckering looks like. That is not a square. Let's try again. That is also not a square, but gets it close enough. So here is our cyclobutane molecule. The two carbons on the left and on the right are the blue carbons in our picture, the ones that sort of moved downward, okay? And if you look down the carbon-carbon bonds, you can see that we're no longer totally eclipsed. We're not perfectly staggered either. This is the best we can do, but we're not perfectly eclipsed, and that's an advantage. Some last time noted that if you look straight at the carbon in the middle, it looks like it's overlapped with the carbon on the other side, and asked, is that eclipsing? Is that strained? We only talk about eclipsing and staggered for carbons that are bonded to each other. This is across the ring, and they're actually far enough apart that eclipsing doesn't matter. So though they do overlap with each other, I wouldn't call that eclipsed or causing any kind of strain. So this is the puckered conformation, and it's, you can imagine probably it flapping like a bat as the carbons on the end are pointing downward versus upward, equilibrating with a couple of different structures. Great question from home, Porter. What is the new bond angle in the puckered conformation for cyclobutane? And the answer is, I don't know, but it's not 90. I don't know how far away from 90 it is. It'd be nice if they gave us a way to look at that. Huh. Volume, ooh, oh, tap on 3. Who knew? I just learned something. That's cool. All right, Porter, we're going to answer your question. 88. That would seem to be worse. Huh. How about that? Let's try 1, 2, 3, also 88. So for cyclobutane, the puckering gets the bond angle a little bit worse, a little bit further away from 109, but maybe that's accounted for in the torsional strain that you relieve? Yeah. Not perfect by any means. And again, carbon for carbon, cyclobutane is less strained than cyclopropane, but more strained than larger rings. All right. Oh, sorry. Now there's some arguing about which questions were good. Yeah, I have the problem of sometimes saying when I see a good question, oh, that's actually a good question, as though the other questions were not, and I don't mean that at all. Torsional strain comes from eclipsed versus staggered, like we talked about last time. Steric strain comes because large groups are bumping into each other. Torsional strain has a component from steric strain, like we saw at the beginning of today's lecture. One aspect of torsional strain is that staggered is more favorable than eclipsed, but another aspect is that, as you noted, some staggered conformations are more stable than others. In some cases, some reactions where you relieve five-membered ring, where you open up a four-membered ring, that can be favorable. In fact, if you've ever taken amoxicillin or penicillin or some beta-lactam antibiotic, the four-membered ring is highlighted there in red, and it's actually opening of that ring that plays an important role in preventing the formation of bacterial cell walls. It turns out that opening that ring provides a driving force for modifying the enzyme that builds the bacterial cell wall so that it can't do what it's supposed to do anymore. And naturally, the bacteria have a great way of dealing with this. They make beta-lactamases that hydrolyze the four-membered ring before it can become a problem. So many of you who have taken antibiotics before have taken this lovely four-membered ring containing compound. All right, a 5-membered ring. We had a bit of a kerfuffle last time trying to figure out what the ideal internal angle would be for a 5-membered ring. There is an equation somewhere. I don't know it, and I should care, but I don't. Nevertheless, we finally settled on the ideal angle in a pentagon being 108. Ideal if flat. Reality is for an sp3 hybridized carbon, again, you would prefer 109.5. So cyclopentane puckers as well. The conformation, the puckered conformation looks something like this. They sometimes call it an envelope, as though these 4 atoms are the sleeve of the envelope, and then that's the flap, only that's not totally how it looks. I don't know that I'll spend a lot of time drawing the envelope conformation of cyclopentane, other than to illustrate that even though there's not a huge amount of angle strain, you still have some torsional strain, though a lot less than in cyclobutane. I'll illustrate this again in Spartan, where we'll draw a pentagon, see if I can do that. And there's our ring. And I'm going to try to orient it in the similar to the direction we did in our drawing. So information angle. So these 4 atoms are not quite in the same plane, but close. If they were in the same plane, the dihedral angle would be 0. And then the other carbon that's pointing downward is out of plane. What that does is it relieves some of the torsional strain. We can verify that the angle is pretty close to 109.5. So it's a little bit distorted from that. If you look down the carbon-carbon bonds, you can see that in some cases the carbon-carbon bonds are staggered. So if we look at the relationship between these 2 protons, that dihedral angle is not perfect, but it's certainly not 0. However, there are some dihedral angles that are basically eclipsed. If you look at this one, that's pretty close to eclipsed. So the molecule distorts itself so that it can relieve as much angle and torsional strain as possible, but there's not an ideal solution. 5-membered rings you're going to see in your DNA and in your RNA. So let's see, nucleic acids. If you haven't seen, yes, that's what I meant. We're going to invent some science. Oh, that's offensive. There's not even a chemical structure. Well, I'm just flummoxed and flabbergasted. Pretty soon it's going to have been faster for me to draw it. All right. Well, sometimes you got to get what life gives you. There's a 5-membered ring there. That is not its conformation. That's just a convenient way of drawing it. But maybe sometime I'll show you the conformation of a 5-membered ring in DNA. That's disappointing. All right, so let's talk about 6-membered rings, because the 6-membered ring has sort of a magical place in organic chemistry. The ideal bond angle for a 6-membered ring would be 120, and again, that's different from an sp3 angle, but the 6-membered ring can pucker into a conformation called the chair. And in the chair, all the bond angles are 109.5, and there is no torsional strain because all the dihedral angles are staggered. So you can think of cyclohexane as being unstrained. And that's unique, and it's just a sort of fluke of geometry, the electric chair. Nice. So let me demonstrate this is the case by drawing a 6-membered ring. Come on. In Spartan. All right, so let's zoom in, and we'll talk about this molecule. So if you look at it from the side, that's why they call it a chair. It's kind of dumb. Look at those 4 atoms, and you can imagine this as being a lounge chair or an Adirondack chair where your head is here and your legs are there, and if you squint and look at it from the side, you can sort of pretend. All right? I don't know why we call it that, but we do. Nevertheless, let's take a look at all of the bond angles. Very, very close to ideal, 109. Let's take a look at all the dihedral angles looking down carbon-carbon bonds. You see staggered, right? No eclipsed interactions all the way around the ring. And so this has minimal angle strain, minimal torsional strain. And because of that, it shows up everywhere in organic chemistry. It's pretty easy to make. And there are a ton of natural products that have 6-membered rings. Sort of a privileged structure. And it's kind of beautiful how each in a 6-membered ring you can stitch together 6 tetrahedrons, and they're all together without any particular angle strain. So this is the chair conformation, and we're going to learn to talk about the chair conformation. Notice that in a chair conformation, you have 3 carbons that are sort of up or above the other carbons, right? I don't know how to describe this other than to say that the bonds between those 3 carbons sort of form a peak instead of a valley. So we're going to call this carbon, that carbon, that carbon up carbons. And the other 3 will be called down carbons. Now, notice on all the up carbons, the hydrogens that are up are pointing straight at us. Or if we look at it from the side, on the up carbons, the hydrogens are parallel to each other and are pointing directly upwards. All right, we will call those axial hydrogens. So these hydrogens are axial to are axial hydrogens. On up carbons, the down hydrogens, the ones that are angled downward relative to the ring, are called equatorial hydrogens. So if you imagine cyclohexane as being a belt around the Earth, the axial protons point to the north and south poles respectively, and the equatorial protons would be splayed out towards the equator. All right, so this proton is equatorial down, this proton is equatorial up. All right, let's spend a little bit of time drawing. And there's some discussion on the chat about A values and such. We're going to get to that. And if I don't answer the question, maybe Emma, you can summarize the discussion. Emma or Brennan, maybe you can summarize the discussion and help me understand what the issue is. All right. So let's learn to draw a chair. You didn't think this was art class. Of course, I'm not going to be evaluating your chair drawings because you're not drawing anything on my exams, at least not that's getting graded. Nevertheless, understanding the chair and being able to draw it correctly will help you get the correct answer on the exams, particularly as we get into reactions. And in Chapter 8, it'll become pretty important. So how do we draw in 2 dimensions what we're seeing here? All right. So I've found it's helpful when doing this to number the carbons of the ring. Now this is kind of stupid for just plain old cyclohexane. So let's actually make it something that's not cyclohexane. Let's make it cyclohexanol. Let's put an OH group there. And all we know from this sort of top-down view is that the OH group is up. We don't know whether it's up axial or up equatorial. So we're just going to pick one and see what happens from there. Now that sounds crazy to you because if you just pick an answer and then see what happens on the exam, things generally don't go very well for you. What I mean by pick one and see what happens is we're going to draw one chair conformation, and then we're going to see that one chair conformation is always in equilibrium with the other chair, which you're going to learn to draw as well. And this allows you to also learn the secret nerd culture, well, especially secret nerd culture organic chemistry joke by which you can identify other fellow nerds if you are one. If you aren't one, then you'll want to forget this joke as soon as I tell it to you, which is, what is the opposite of a chair? And the answer is the other chair. You try this at home, or pickup lines, or various things. I don't know. You will find people that will laugh. And most of them will be at you, but some might be with you, and then that's how you know they are fellow nerds. So we're going to number around the ring, 1, 2, 3, 4, 5, 6. To draw a chair, let's start with atom 1, and we're basically going to draw a tetrahedron. We're going to forego dashes and wedges. I'm going to draw one line straight up and down, another line pointing out sort of towards us in this direction, another line pointing downward to our right, and another line pointing downward to our left. Just tetrahedron. We would use dashes and wedges before, only we're not doing that here. Okay? And for carbon 1, the group that is up, this will be carbon 2 and this will be carbon 6. The group on carbon 1 that is up is the OH group, and the group on carbon 1 that is down is the hydrogen. All right. Okay so far? All right. So what do we do for the bond between carbons 2 and 3? We're going to make the bond between 2 and 3 be parallel to this carbon-hydrogen bond. Note that those two are parallel. Similarly, we're going to make the bond between 5 and 6 also parallel to this CH bond and to the bond between 2 and 3. So I'm going to move our number 6 out of the way a little bit and draw about the same length, pointing in the same direction. Just to orient you top down, what we're saying is that those bonds are parallel to each other. And this is general. A carbon-carbon bond in a chair conformation is going to be parallel to the bond directly across the ring and parallel to the CH bond that is adjacent. Okay? So now filling in the rest of the details is just about drawing parallel lines. The bond between 3 and 4 needs to be parallel to the bond between 1 and 6. And then the bond between 5 and 4 needs to be parallel to the bond between 1 and 2. Straightforward enough. So you may want to practice that. All right, so now let's fill in the rest of the details. Carbon 1 is an up carbon because it's pointing upward. Carbons 3 and 5 are also up carbons. And on up carbons, we're going to draw a line straight up. The up substituent on an up carbon is up axial. So this is a general principle. In cyclohexane rings, up carbons have up axial protons, or I suppose if we want to be general, we could say substituents, by which we mean proton or other group. Similarly, up carbons, the down substituent on up carbons is equatorial. How did we know where to draw those equatorial hydrogens? That's the tricky part. Drawing things straight up and down is easy. The carbon-hydrogen bond involving carbon 5 is going to be parallel to the adjacent carbon-hydrogen bonds. Similarly, the bond between 3 and its proton, equatorial proton, is going to be parallel to the adjacent carbon-carbon bonds. And then we can do the same thing for the down carbons, which I guess I'll highlight in this crazy green color. And in general, we can say that down carbons have down axial substituents and up equatorial substituents. All right. Questions so far? Good joke for a first date. Someone volunteers as tribute to give that one a try. Okay, yes, let us know how it goes. Da, 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 da. Maybe I'll try that one. Have I tried that one on Amber? We've been married 20 years, so I doubt I would even get a reaction to that kind of thing at this point. All right. So last hour, somebody asked, well, okay, you've got that OH group that was up axial. How did I know that it needed to be up axial? And the answer is because I arbitrarily chose to make carbon 1 an up carbon. Had I chosen to make carbon 1 a down carbon, whoa there. Had I chosen to make carbon 1 a down carbon, then at this down carbon 1, what is the up position?
The hydrogen.
Well, going back to my structure, carbon 1, the up group is still the hydroxyl, but I've only got 2 positions at carbon 1. One is up and the other is down. And this is an important principle. Up stays up and down stays down. We haven't popped the OH group off and put it on the downside of the molecule. It's still pointing upward. Only here, instead of being up axial, it is up equatorial. Now carbon 1 is a down carbon. And like a down carbon, it has a axial down substituent and an up equatorial substituent. Notice that, and it turns out you can interchange these two choices by simple rotation around sigma bonds. You don't have to break any bonds to get the up axial OH group to be in an up equatorial position. This is the other chair. Waiting for the other chair to drop. Maybe that's another one to try. Sounds a lot scarier than the other shoe dropping. All right. Look at what happened as we go from one chair to the other. All the carbons that used to be up are now down, and all the carbons that used to be down are now up. Yes?
How did you know that the OH group needs to be up instead of down?
Well, I'm using, that's a great question. How did I know the OH group needed to be up instead of down? And someone's asking, why isn't the hydroxyl axial down in the other chair? I'm choosing to keep this molecule in this orientation with the OH pointing up toward us, not flipping it over. And so when you go from one chair to the other chair, you can't actually make that hydrogen, make that OH go onto the other side. It's a little tricky here because actually, if you drew the molecule this way, that's actually the same thing, just do a pancake flip, and it is. So I suppose to illustrate your question, we could think about the following situation. Let's maybe put an OH group here and a no, I don't want to go that crazy, a methyl group here. And then consider the two chairs that you would make from these two options. Those two are different molecules. They're actually called stereoisomers. This is the trans isomer and this is the cis isomer because here OH is on the opposite side of the ring as methyl, and here they're on the same side. We can draw two different chairs for these each of these molecules, and then we can choose which one is more stable. We'll just, I think, probably have time for the first chair. So I'm going to choose to put carbon 1 at an up position, and the up substituent on carbon 1 is a hydroxyl group. Then on carbon 4, I've got a down substituent, which is methyl group. Now, I could make the other chair, and to make the other chair, all I have to do is move carbon 1 to a down position. OH is still going to be up, only now it's up equatorial. On carbon 4, methyl group is still going to be down, only it's down equatorial instead of down axial. When changing from one chair to the other, up stays up and down stays down. But, hold on, I guess that is a little bit confusing, isn't it? Because when you go from one chair to the other, up carbons go to down carbons. The switch from an up carbon to a down carbon, thinking about the atoms of the ring, but up substituents, by that I mean groups coming off the carbons of the ring, stay up. Down substituents stay down. But axial and equatorial interconvert. So, yes, this was an up carbon. After the interchange between chairs, it becomes a down carbon, but the group that was up is still up here, only it used to be axial and now it's equatorial. So what we're going to do is we're going to start drawing a chair for a molecule, knowing that there is another chair out there, just like there was another Skywalker. See, weekly Star Wars reference, you're welcome. You draw both of the chairs and then you see which one is more stable. And we'll talk about how to assess that next time.